So recently I've been working a lot with the PEFT library because I've been fine-tuning LoRA and DORA and RS LoRA models as part of a research project. And it's been really interesting to kind of understand some of these details about how these models behave. So one thing that I came across was that merged and unmerged LoRA models produce different outputs even though they're given the same inputs. So I'm going to walk through the process I went through for debugging this issue. And I made a previous video where I walk through the merge and unload internals to understand how the PEFT library merges LoRa adapters into the base model. And that's a separate video if you want to look at that. I'll try to remember to link it at the end of this video. And there was nothing internally happening inside merge and unload that showed me why this difference occurred. So I'm like, okay, it's not something in the library. So what is it? And so I'm going to walk through that journey and what I learned from that. So the first thing I'm going to do is I'm going to show the model outputs. And here I am loading the base model, which is small LM2 135 million. I'm loading the adapters. I am making a copy of the adapters because when I do adapters load, it's going to overwrite my adapters with the merged model. So if we look at adapters copy, we can see we have the unmerged LoRa weights. And so this linear layer for QProj, for example, this linear layer has a base layer, LoRa dropout, LoRa A, LoRa B, and these three are empty. So that's what a linear layer looks like. And then if we look at adapters, it has now collapsed because it has been merged into the base model. So QProj is a single linear layer with one weight matrix instead of having a LoRa weight matrix and a LoRa B weight matrix and a LoRa dropout. So those are some setup steps. If we look at yeah, nothing noteworthy there. All right, so I'm going to create some random inputs. I'm going to use integers so it replicates the tokens that would be passed through the model. And 49,152 is the vocabulary size for small LM2 135M. And we're going to assume we have two inputs, and we're going to have 576 embedding dimension. So we're assuming that we're passing our embedded tokens into the model. Okay, cool. So key thing here, you want to make sure to always do .eval because otherwise you can get false negatives even though two models are the same, two models are the same and you expect the same output. If you don't do .eval, it will not turn off the dropout layer and you'll get some non-deterministic behavior. And so I have my merged model. I'm going to pass my input, and then I have my adapters copy, and I'm going to pass my input. So we're going to pass that through, and we're going to look at the shape. So we get 2 by 576 by 49,152. So this turns out to be 56 million values. So now we can do torch.allClose, where we look at merged out and adapter out with these tolerances, and this returns false. And if we take a look at these output tensors, if we look at this here, 6.4688, 6.4375. So already we can see about a 0.02-ish, 3-ish difference. And then here we see a 0.03, almost 0.04 difference. Well, no, not really. 0.03, I think. Here's another 0.02 difference. So yeah, we can visually inspect and we can see that okay, these outputs are not the same. If we look at the maximum output and the maximum difference and the mean difference between these two tensors, we can see that there are some values where the difference is 1.125, which is obviously significant given that some of these values are between 0 and 1. And the mean difference, the absolute mean difference, is about 1/10 of one of these activations. So these logits are, considerably different. And I'm going to run this scatter plot. I'm going to do it on the first 1 million values because 56 million is too large for this T4 instance and it crashes out the RAM. And then I have to make sure that it's in float 32 and the size of the marker, and I've turned alpha on to 0.2 so we can better visualize the discrepancy between these two tensors of logits. So we can see we would expect straight line, right? Because at least I expected them to be equal because I'm like, okay, I'm using the same LoRa adapters, I'm merging them, so why are they not the same? So this is kind of setting up the problem and the motivation for this deep dive. So one thing that I noticed along the way, which is if I convert the models to float 32 instead of BF16, and then I run the same kind of forward pass through the model, it's still different, right? They're still not equal, but the differences are much smaller. So it's about 5 times smaller in terms of the maximum difference and the mean difference. And then I'm going to run plot scatter again, or I guess pyplot scatter. And okay, it's a lot less. There's a lot less variance, right? So it's getting closer to a straight line. There's still some deviation, but it looks better than this bulge that we see here in BF16. So at this point, you might already, you can kind of tell where this is going, or at least this is a hint that, okay, changing the precision changes the outputs and makes them closer. So spoiler alert for this video, we're going to find that this is in fact a floating point precision error that's propagating throughout the model. We're going to run the same forward pass, but I'm going to do it just through one layer. So the merged model has a single linear layer when we look at the self-attention QProj. And then the adapters has a LoRa linear layer, which has all these different components. And so here we're going to start visualizing that a forward pass through a single linear layer with a single weight matrix, and a forward pass through a LoRa layer with 1, 2, 3 weight matrices is going to cause the outputs to be different. So this time I'm going to do floats. So I'm going to use rand n instead of rand int. And then I'm going to run this code. So again, I set it to eval mode, and then I pass it through the QProj layers, and then I look at the output shape. We look at the merged out, and we can see visually, okay, yeah, there's some differences between these two. Torch all close is false, and it's a significantly lower difference, right? So we went from, this is, let's see, let me make sure, what is this? Adapters, copy, detype. So these are float 32 models, and we went from 0.02 mean difference when we're passing through the entire model down to about 0.01. So we have half the difference. But the thing is, this is only one layer, right? So we're only passing through one QProj layer out of the 30 that exist. So it makes sense that we have a smaller difference. And then run this, and now we have, I use the smaller tensor as input, so I don't have to index a subset. I can look at the entire tensor. And visually, this, it's hard to tell that there's a lot of variance between the two, right? This could very well just be the fact that there's a lot of, values that are close together. While we're looking at this, I think it is interesting that, the distribution of values is concentrated here. So I guess it looks like a somewhat normal distribution. Maybe it's not, but we have a high concentration of values in the middle, and then it gets sparse as we get to the tails. So that's kind of interesting. Okay, so that sets up the problem, and it kind of gives us our first glimpse into what the issue could be. But along the way, some of the other things I was trying was to figure out if this was an issue with, the weight matrices themselves. Was something happening during the conversion, during merge? Was that causing a floating point difference? Was it the matrix multiplication between the weight matrices and the input? So I'm just going to go through some of these experiments that I ran and kind of show how I eliminated some of these other possibilities uh, from consideration as the source of the problem. So I'm going to do this a lot. I'm going to reload my base model adapters copy and merged model. I'm going to look at the first layer, self-attention, qproj. I'm going to grab the self-attention module. So if we look at adapter module, here we have all of our unmerged layers. If we look at merged module, we have all of our merged layers. Then I'm going to grab the layer itself. So this is a LoRa Linear layer for the adapter and a single linear layer for merged. And then same thing, set it to eval mode and get the outputs. Now in this instance, I'm actually not looking for outputs. I want to compare the weights. So what I'm doing is I'm manually merging the LoRa adapters into the base layer weight. So I grab LoRa B and LoRa A and the scaling factor, take the matrix product between LoRa B and LoRa A, and then multiply it by the scaling factor. This is just an integer, or a whole number, 2.0. And then the final adapter weight is going to be the adapter layer's base layer weight plus this delta weight. So I'm kind of manually merging so I can see, like, is there something, my curiosity or my hypothesis was like maybe there's something happening in this manual merge that's causing the weight difference. And maybe that weight difference is causing the output difference between the unmerged and merged models. So we have our merged layer weights and now my manually merged final adapters weights. But in this case, no, they're actually the same. So it was not an issue of the merging operations causing this deviation. And one thing I'll note here is that looking at this chart, when we were looking at a single output for qproj and we were looking at float32, this chart here looks very similar to this chart here. In fact, this actually looks like it has more variance than this one, even though torch all close is true. So just noting that. I also used a higher alpha. So if I go to 0.2 to kind of compare apples to apples, so here we have this, and here we have this. This one still looks actually less varying than the true comparison. And I have this layer names dictionary where I have all the self-attention modules that have LoRa adapters and all the MLP modules. And I'm basically iterating through all 30 layers. I'm looking at each of these two modules. I'm grabbing the module from the adapters and the merged model. And then I'm iterating through each of these layer names, grabbing the layer, setting to eval mode, and then recreating the merging operations. And if the merged layer weight is not equal to the final adapter's weight when it's converted to torch BF16, then add the layer index module and layer name to this diffs list, and then return the diffs so I can list out and see what the differences are. So if I run this, the differences are 0. So what this is basically saying is that there is no loss of information between or during the merging process from LoRa adapters to final merged weight. So for me, that eliminated that as a source of this discrepancy, because if the matrices are the same, then that's not the source of the error. So that's the first thing I looked at. And let's collapse this. Next, I looked at the matrix multiplication between a set of inputs and the weight matrices. So I'm like, is there something happening in the matmul operation for whatever reason? I don't know. I was just kind of throwing darts, wherever they land and seeing what's stuck. So I'm going to still use my final adapter's weight and my merge layer weight. And I'm going to perform the matrix multiplication between the input and the weight matrix. And if we look at that, it is also true. So this was just for one layer. I'm going to repeat the same process for all layers and all modules and all layer names inside each module. I'm going to grab the LoRa weight matrices. I'm going to calculate the delta weight and the final weight. And then I'm going to calculate the adapter output and the merged output. And if it's not similar, then I'm going to gather the information about where they're different. So let's do a refresh of our models. And the length of differences is 0. So, okay, it's not the matrix multiplication between the input and the weight matrix. So what is it? Well, this is where this is a little bit of a post-hoc analysis, but we're gonna see, as the title shows, that the forward pass is actually where this difference is. So I'll actually come back to this here, but one thing I do want to show before we dig in is we're gonna look at the LoRa linear layer forward pass. And if the adapters are disabled, then the result is the forward pass through the base layer. So this is kind of our baseline. If we weren't using LoRa adapters, the result would be the base layer's output. Otherwise, if we are using the LoRa adapters, we first grab the outputs of the base layer, that's result, and then we go down here and we add to the result the output of our inputs going through the dropout layer, going through the LoRa A layer, then going through the LoRa B layer, multiplied by the scaling factor. In eval mode, the dropout is not used or is disabled. So there's LoRa A forward pass, LoRa B forward pass, and then base layer forward pass, and the addition of those outputs. So, there's 3 or 4 matrix operations that are happening if we are using our LoRa adapters. Whereas if we're not using our LoRa adapters, there's a single forward pass happening, single matrix multiplication happening. And so my understanding, based on what I've looked at, is this is the cause of the discrepancy in the merged and unmerged LoRa model outputs. Because for the merged model, we have 1 matrix operation. For the unmerged model, we have 4 matrix operations. So let's visualize that here. So basically what I'm going to do is, this is much of the same code as above, except, now I'm grabbing the module, grabbing the layer, setting up my input based on the layer size, layer weight size, and then I'm doing a forward pass in the merge layer, a forward pass in the adapter layer, and then comparing those outputs. And I want to see the diffs, so I'm going to look at, what the layer index is. So I'm going to run that. I'm going to get my fresh set of models. And we run this, and we get 210. And one thing I'm going to do here actually is I'm going to add module and layer name. And if we look at these diffs, we basically have 1, 2, 3, 4 layers in self-attention, 3 layers in the MLP. So we have 7 layers, and we have 30 transformer blocks in the model. So 7 times 30 gives us 210. So it's all of these LoRa adapter forward passes that are different from all of the merged layer forward passes. More as an exercise, I took that same code And instead of doing a forward pass, I did all the steps that we see done here, except for dropout, because I'm not using dropout. So I passed the inputs through the LoRa A, which is done here. Then I passed that through LoRa B, which is done here, and then multiply by the scaling output and add it to the base layer. So forgot to mention that here. So first thing is base layer output, store that here, get the LoRa output, add the two, convert it to the right data type, and then do the merged output, which is the forward pass in the merged layer, and then compare those two. And I should add module and layer name to this. Get a fresh set of models. And we get the same, 210. So at this point, I was pretty sure that the difference is between the forward passes. And that's really interesting to me because conceptually they're the same, but computationally they are not, right? One matrix operation versus four, that compounds these floating point differences throughout the model. Just as a check, I went through all of the other forward passes that are available to us, and I compared the merged model and our adapter's copy. So if we look at token embeddings, the output of the token embeddings layer is the same. The input layer norm for all 30 model layers, the output of that between the merged and unmerged models, that's the same. All 30 post-attention layer norm, they're equal. The final layer norm outputs are equal. The rotary embedding outputs are equal. The LM head, the final LM head, at the end of the model, the forward pass through that gives outputs that are equal. And then just for completeness, the outputs of the activation function in our MLP layer for merged and unmerged is equal. So just to be thorough about or comprehensive about what we're looking at, none of the other non-adapter forward passes are causing this issue. And then as a final check, similar to what I showed at the very start, I'm going to look at what are the differences between the outputs given different data types. So we're going to use bfloat16, and then we're going to use the more precise float32. So when we first load this, everything should be bfloat16. I'm going to grab my layer, get my inputs ready. For BF16, I'm going to pass bfloat16 inputs. And then for F32, I'm going to pass F32 inputs. And then I'm going to compare the results. So for BF16, the max difference was 0.125. For float32, it was 0.07. So, more than 10 times smaller. And while we're looking at that, let's just grab this. And let's look at the mean. Grab this. Look at the mean. And again, we still, we have that 10x difference between BF16 and float32. So the fact that changing the floating point precision changes the difference of the outputs, that itself I think is a key indicator that this is a floating point error issue. And then of course we looked at it more systematically, and we looked at these forward pass differences, and we saw that it's every single forward pass between the merged and unmerged layers is different. And here was Claude's analysis. So in weight comparison, we're comparing two tensors that were created through a similar process, and really the exact same process, taking the base layer, multiplying the LoRa adapters together, multiplying that by scaling factor, adding it to the base layer, and getting the final weights. The matrix multiplication, I did a single operation with identical inputs, and since the weight matrices are equal and the inputs are equal, the outputs are going to be equal. However, in the forward pass, the merged model has a single operation, whereas the adapter has 3 to 4 operations, minus LoRA dropout because we're in eval mode. And so yeah, this adapter model introduces multiple rounding points because of these multiple operations. So that was I guess the solution to my problem, and this let me know that it's nothing that is happening during the merging process that's causing this issue. It's just the very nature of how these two models are structured and the difference in matrix multiplication and addition operations that is causing the floating point error to propagate throughout the models and cause a difference in the final outputs. So again, I made a previous video on doing a deep dive in merge and unload, which is a LoRA model method in the PEF library. So I'll put a link to that. And then I'm going to do one more video where I talk about how I used register forward hook to kind of look at how this floating point precision error propagates layer by layer as the inputs pass through the merged model and as the inputs pass through the unmerged model. So thanks for watching, and I'll see you next time.